All right, so let's go ahead and get started. So we are looking at assignment 9 here, and Dervin just had a great question about 9B. We are not doing that. We're just doing this volumetric analysis, titration of a solid acid. So this would be an unknown for you. It's not going to be this time because everybody's going to get the same data. But here what would happen is I would have asked you to bring me a test tube with your name and your partner's name on it on a piece of tape, and I'd give you enough for 2 trials, and you would be using your own, not NaOH, but we would have made KOH. So you would have had your KOH that was in the glass jar that you determined the molarity for in lab 8, and you would be using that for the titration. So normally at this point, I would tell you to be careful not to use too much of the KOH because you don't want to run out of it. Not a problem today. All right, so this is a solid acid. So here you would have to dissolve the acid. The first thing I would have you do, and let me zoom down to, I'm going to pull up your sample data, and the sample data is already posted on Canvas in the lab notes section. So there we go. All right, so the first thing I would have you do is take your Erlenmeyer flasks into the balance room, and I'd have you weigh them empty, each of them with a label on them so you know which one's for trial 1, trial 2. Then I'd have you go out to your lab bench top, and I would have you add approximately half of the sample that I gave you into one flask and half into the other. So you would get your masses that were the flasks empty and then the flasks with half of the sample. It doesn't have to be a perfect half. In this case, you're going to find it's not perfectly half. That's okay. So once you have your solid into the flasks, you would need to dissolve it, and it says simply dissolve the acid in 40 to 60 milliliters of water, and that word simply, it's almost a bad joke because some of them dissolve really well and some of them don't. Some of them do need to be heated, and that's what it says right here. So some unknowns may require heating, and the tough thing is that if you heat too much, of course, the water is going to start evaporating and then you actually have less water. So sometimes if you get one of those tricky unknowns, it can be a challenge to get it to heat. I have select out only the ones that go into water well, because I know at night it is tough to be playing around with getting this acid to dissolve. So I normally do select out the choice unknowns for you guys. But just to let you know, this is what you would be doing, and it really doesn't matter how much water you add because the acid's coming in solid form, very similar to that KHP last time. We just have to get that acid dissolved. And also, just like last time, you'd use the indicator phenolphthalein so that after titration, it would turn pink. So let me just review your burettes with you. So what you would do with your burettes is you would rinse it once with your KOH solution, remembering to only put a small amount in, and then you're going to roll it around. My fingers do not look like they're rolling a burette, but if you remember from the video, they did a great demonstration of rolling that solution all the way through the burette, letting some go through the tip. Then you would fill it near the zero. Doesn't have to be a perfect zero. You'll notice on your sample data, I did not give you perfect zeros. Then you're going to clear the bubbles, which are really important to get good data. You'll record your initial volume with 2 digits after the decimal. You're going to titrate till you get that light pink. Then you'll record the final volume. And then you would rinse 3 times with distilled water. Then you'd come up and show me your burette. I'd have you touch it to pH paper to make sure it didn't have any more base in it. And then I would send you over to place it gently and lovingly into our crate of burettes. All right, any questions about what you would have done with your burettes tonight? All right. So the first part of this experiment would be to titrate it till you get to that light pink with phenolphthalein. But there is a second part, and it's kind of an optional second part. I shouldn't say most. I should say every semester my students have opted not to do that optional part, but I just want to tell you what it is, and that would be back titrate, and I like how they use the word simply. So the idea of back titration is you may overshoot your endpoint. every once in a while, and if you've ever done a titration, you know how easy it is to do that. Suddenly you weren't paying attention and boom, it goes bright red, bright pink, and you're like, oh man, I added like 3 drops too many and suddenly it's bright pink. I wish I could go back a little bit. Well, that's what we do with the back titration. So normally we would set up a burette of HCl. It would be all set up. It would be over on the side next to that window. And if you felt you needed some HCl because you wanted to essentially back titrate, kind of give yourself a little bit, another chance to get to that perfect endpoint, you could. And so that is what we would do with back titrate. The idea is you've overshot your endpoint, and now you're going to very slowly go back with HCl to find that perfect light pink color. So in the sample data, you'll notice I've crossed that out, and that's because, again, I've never had anybody who decided they wanted to do that. Once you've done lab 8, most people get pretty good with their titrations. Also, because you've added a lot of water here in order to dissolve your unknown, these ones have more of a tendency to be light pink than that shocking pink that you would have seen with lab 8. With lab 8, you have a strong acid and you have a strong base. Here you have a weak acid with the strong base. So again, you don't tend to see that shocking pink with this one anyways. So it seems to go very well. All right, so that would be your experiment. Let's talk about our class data. So just like last time, I'm going to ask you to write this, write the data sheet, the data below on your own sheet. So this comes out of your lab notebook that you got from the bookstore. If you don't have that, just write it on another piece of paper. All right, and in the very top box there, this one right here, it says concentration of, on yours, they should have updated this in the lab manual, so I'm hoping yours does say KOH. This is an old one that I have that says NaOH. So concentration of KOH, this is your molarity from lab 8. So make sure you write in your molarity. Since we happen to use the same one for the entire class, the same data set, everybody should have the same molarity. I put an X through the molarity of HCl because, again, I don't think I've ever had a student who chose that option of back titrating. Here you're going to see I gave you data for 2 trials. The very top is the mass of the flask, and the second one is the flask plus the sample. Then underneath it, you have your final burette and your initial burette reading. It's a little weird this time. The way it's set up is the initials on the bottom and the finals on the top. The nice thing about setting that up is it makes it really easy to do your calculation here. So subtracting 22.51 from 1.10, and boom, it goes right there into the volume of KOH. The other thing that I'm going to warn you about is because, at least on my page, milliliters are missing right here. You've got to get those milliliters in, otherwise you don't have any units. Previously, the grams were already in there, so you could just write the numbers. But I do need you to indicate that these are milliliters. You could either do it on the side there, or you could place it in here. I think it's easier to do it off to the side. All right, questions on anything so far with that sample data? Oh, is trial 2 in the... Oh, you were right, thank you. So Andrew mentioned that I mixed up the ordering. Yes, I forgot this lab has a weird order. So the initial should be 0.5 and the final should be 24.05. Thank you, Andrew. And then Jervin, what was the question there? I see for which trial, 1 or 2? So Jervin, when you get a chance, let's see. Oh, you're going to ask later. Okay, no worries. Okay, other questions on this data set so far? Okay, so make sure you're writing it into your own data sheet. And Andrew's asking about the KOH concentration. Yes, it is the average. So let's go back to lab 8 for a second. And yes, it is going to be this average right here. All right, other questions so far? So again, you're going to write it onto your own data sheet, or if you don't have a data sheet, write it onto a piece of paper. And this is available in the lab notes section. It's titled Lab 9 Class Data. And I'm going to show you how to do the calculations next, but any questions? All right, so let's go ahead.
Professor,
yep.
Did you change, like, when you crossed out the mass test tube plus sample and the mass test tube minus sample, did you just change what would be filled into those boxes?
Yes, so normally, the way this was written once upon a time, where it says mass of test tube plus sample, said mass of test tube plus sample and mass of test tube minus sample. First of all, everybody got confused about the minus and the plus there. But the other thing was you were trying to weigh a test tube like so on the balance, and it would either roll off or you would put it in a beaker like so, and it just got very complicated. So instead, what I have everybody do is weigh the flask, and then I have you weigh the flask with your solid. Yeah, so that we don't have to worry about the test tube rolling off or anything. So yeah, that's all I changed. Okay. Was that your question from before, or?
Yeah, because it looks kind of like, yeah.
Yeah, okay, yes, so that's for trial 1 and for trial 2, where the mass of the flask, mass of the flask are these right here, and then the mass of the flask plus the sample are those right down there. All right, so any other questions so far from our Lab 9? Okay, so let's start talking about our calculations. All right, so this is very colorful. I apologize for those of you who don't like the colors. So let's start up at the top. So remember this value that I have here, 0.500, that's just a sample value. You're going to use your own, and it's the average KOH from last class. So when you see the calculation below, make sure you replace 0.500 with your own value. And here I did a worked example, so let's just go through this. So here I have the mass of my flask and the flask plus the sample. So I subtracted them to find this 1.0945 grams. Then I took the final reading of the burette minus the initial reading, and I got the volume of KOH used, that 18.35, which went below 18.35. So any questions so far about what I did up at the top? All right, so then our mass of sample, this 1.0945 grams, that came from the top. That is this one right over here. So that's the difference between the flask and the flask plus sample. Next up, we need to know the equivalent or the moles of KOH. And how you're going to find that is right below here. So you're going to take the volume of your KOH, which we found right here. It is now right down here, 18.35, and you're going to convert it into liters. If you want to convert it to liters in your head, that's perfectly fine. And you're going to multiply it times your molarity. And again, remember, it's got to be your molarity, not this 0.5 here. And that's how you're going to get that 9.7, or in this case, 9.175 times 10 to the negative third moles. It's this value right here. And I know I'm going through this kind of fast, but any questions on how you're starting with your volume of KOH using your molarity to find the moles of KOH? All right, so the next one, and this is probably one of the more tricky ones, is the equivalent or moles of the unknown. What we're looking for is moles of H+. So when we're dealing with equivalence, this is very similar to dealing with normality. So today we're looking at moles of H+. So we're just trying to figure out how many moles of H+ are in your acid. And the way we set up this equation is that for every 1 KOH, there is 1 H+. And so it will end up generating water and K+. But the important part for you is that it's a 1-to-1 reaction. And if we looked at it as a net ionic, it would be 1H plus 1 OH minus forms water. So I'm going through all of this with you, but it's going to work the same as it did last time. And that is, once you know your moles of KOH, you also know your moles of H+. Since it's 1-to-1, however many moles you find of KOH, the identical number of moles are the H+. So any questions about that? You did that with Lab 8 as well. They should have identical number of moles because they're 1-to-1. Okay. So that is why you're going to see the moles that I have here. Here is my KOH. And here are my equivalent moles of the unknown. These are the moles of H+. And those numbers are the same. They should be identical for everyone, again, because it's a 1-to-1 reaction. So any questions about finding those equivalents or moles of the unknown? All right, so next up is the equivalent weight of the unknown. What you're going to do is take the grams, which were found, let me try a different color here, right up here. That's your mass of the sample. And then you're going to divide by the moles we just talked about, right over here. So it's grams of your compound divided by the moles or equivalents of H+. That will give you the equivalent weight. So is this an equivalent weight? It's not exactly a molar mass, and the reason it's not a molar mass is because we're not sure if it's moles of acid or moles of H+, because we don't know if you have a monoprotic, a diprotic, or a triprotic acid. So all we can say is this how many grams of acid per moles of H+, and that's why it's the equivalent weight and not the molar mass. So any questions on anything there? Let me get some of these colors out of our way. Oops. All right. Okay, so next up, you're going to find the equivalent weight average. So you are just going to average trial 1 and 2, just like you would in any other class. Trial 1 plus trial 2 divided by 2. And then you're going to find the percent difference. So the percent difference is right over here. Let me try a different color. Too many colors going on. Sorry, just cleaning up a little bit here. There we go. All right, so trial 1 minus trial 2, so we want to find the difference between those two, and then you will divide by the average, and remember you found the average right up here, and then multiply times 100. That will give you your percent difference. You're looking to see how different trial 1 and trial 2 are. So any questions on anything here with the percent difference? Okay. All right, any questions with how you're going to fill out your data tables? All right, so let's go ahead and talk about the post-lab questions, the discussion questions. And the first thing I want to do is talk about equivalence and normality. So we started talking about this last lab. And what we said is for an acid, it's moles of hydrogen per liter, and for a base, moles of OH per liter. So we took a look at sulfuric acid, and we said sulfuric acid breaks up into 2 hydrogen and 1 sulfate. So we could do a conversion here where we say 3 moles per liter of sulfuric acid, that's 3 molar. We could multiply it by the conversion factor, 2 moles of hydrogen divided by 1 mole of the acid, and it would give us 6 normal sulfuric acid. We could do something similar for aluminum hydroxide, which is a base. So if it is 5 molar, we could take 5 moles per liter and then convert 1 mole of aluminum hydroxide into 3 moles of hydroxide, and we would then call it 15 normal aluminum hydroxide. So any questions on this part right here? We went over some similar examples last class. All right, so now this is straight from last class. I just went in and copied it over. So I feel like this is an easier way. This is kind of the longer way, so I did want to show it to you so you see where everything comes from. But last class we said it's molarity times the number of hydrogen will equal normality for an acid. So for our phosphoric acid, which has 3 hydrogen, we did 2 molar times 3 gave us 6 normal. So any questions on how we did that phosphoric acid? All right, so next up for our 5 molar HCl, 5 molar times 1 hydrogen would give us 5 normal for the acid. All right, and finally for our sulfuric acid, we did 7 molar times 2 hydrogen, gave us 14 normal. So any questions on how we were finding normality through this method here? All right, and I can't remember if we did bases last time or if this was a new thing that I added, but here we have barium hydroxide. So 2 molar, and we multiply it by the hydroxide for base. So 2 molar times 2 hydroxide gives us 4 normal, and 5 molar times 1 hydroxide for NaOH gives us 5 normal. So any questions on how to convert between molarity and normality? So Jervin has a great question, and excellent. So I hear that we did do all those examples. Excellent. So I did just want to review that with you. Jervin has a great question, and I'm going to cover that next. But any questions so far? All right. So equivalence and normality are very similar. So what we're going to say is in 1 mole of H2SO4, there are 2 equivalents of H+. So when we're talking about the equivalent, it's very similar to talking about normality, but it's not usually talking about the overall concentration of the solution. Instead, it's talking about something specific in that solution. So whether we're talking about hydrogen or hydroxide, we're talking about something specific there. So for every 1 mole of sulfuric acid, there are 2 equivalents of hydrogen. For every 1 mole of phosphoric acid, there are 3 equivalents of H+. All right, so questions on anything here so far? And I apologize if those of you who are like, oh, this is obvious, I already know this. I am actually going somewhere with all these examples. All right, so NaOH breaks down into 1 sodium and 1 hydroxide. So in every 1 mole of NaOH, there'll be 1 equivalent of hydroxide. All right, so why we did all of those is 4A. So 4A, when you first see it, it looks really complicated, but it's not nearly as bad, especially since you are all now experts on normality and equivalence. So here, what they want you to do is give the number of moles, which is 1 equivalent. And that's kind of a strange way to word things. So I want to show you what we mean. So if we're looking at citric acid, here is citric acid. So it's a long formula, but notice for all of these, the hydrogens are going to be bolded. And I've gone ahead and circled this one. So there are 3 hydrogens inside of here, or I should say 3 hydrogens that can be given off during a titration. So now underneath, I say for every 1 mole of citric acid, there are 3 moles of H+, and that is equal to 3 equivalents of hydrogen. So for every mole of citric acid, we have 3 equivalents of hydrogen. Unfortunately, that's not the way the problem is asked. They say if there's 1 equivalent, how many moles of citric acid do you need? So what I've done is divided both by 3. And now I can say for every 1 equivalent, there are 1/3 mole of citric acid. So I know that's a really weird thing to do. We'll do another example together. But any questions about this citric acid? Okay, so I want to try another one with you. Let's do oxalic acid. So this is D. All right, so again, the hydrogens that you're supposed to be looking at should already be bolded. And I know sometimes with the font it's hard to see, but these are our hydrogens here. And this is oxalic acid. I think I misspelled oxalic. Yes. Oxalic acid. There we go. All right. So for every 1 mole of acid, how many equivalents will there be? So for every 1 mole of our oxalic acid, how many equivalents of hydrogen? Excellent. See lots of 2's coming in. Any questions about that 2? It comes directly from this 2 right here. All right, so again, this isn't the way the question asks it. The question says, what if it was 1 equivalent? So now what you're doing is you're dividing both sides by 2. So for every 1 equivalent of H+, you need half a mole of this acid. So any questions on how we're finding the number of moles here per equivalent? So this is tricky to get started, but once you get started, it's not so bad. And sometimes students ask, do I have to show the calculations? And no, I don't need to see the calculations. What most people do, which is perfectly fine with me, is they write their answers just off to the side here, just the way I did my, just the way I did my 1/3 here, and that's perfectly fine. If you'd prefer to do it on another page or somewhere else, that's okay as well. But any questions on how to answer this 4A? All right. Next up is B. So it says a molecular mass of an unknown acid is found to be 220. I'm changing it to 220 with 3 sig figs. Just gives you a little bit more sig figs here. Calculate the mass of acid that would neutralize, and here's your problem here, 12 milliliters of 1.10 molar NaOH. And here are the formulas of the acid. So H3X, you could think of it also as H3A, that is a triprotic acid. And then you have H2X, which you can also think of as H2A. That is a diprotic acid. They both have the same molar mass, that 220, and I'm going to put in that decimal point. So it is 3 sig figs. And I've done the first one, or at least I've set up the first one for you. So here it says H3X. I know X must be a 3 minus because there's no other reason we would have a 3 right here. So because X is a 3 minus, and this is a triprotic acid, I've reacted it with 3 NaOHs. You're going to get 3 waters, and you'll end up with Na3X. And again, the reason I knew about this 3 is because I knew it had to have a 3 minus because there was 3 hydrogens. All right, any questions on how I set up the chemical reaction? Oh, I do see a question coming in for Juan about the previous one. It's up to you. You can leave it as a 1/2 mole or convert it to 0.5. Most people leave it as 1/2 just because it's one less calculation to do. Because you're going to have 1/2s, 1/3, and all sorts of stuff. But yes, you're welcome to leave it in fraction, or you can convert it to a decimal, whichever you prefer. All right, so any questions so far on this part B on how you're going to set up your equation? Okay, so again, I've set up the first one with the triprotic acid, but you'll need to set up the second one for the diprotic acid. And underneath, here you know about your NaOH, you know its volume and its molarity, and I recommend you start with its volume. So you're going to start with that volume and you're going to use molarity to get into moles. Then you'll use your mole ratio to get into the moles of acid, and then the molar mass, which was given, this right up here, that will get you into grams of the acid. So it's a challenging problem, but I know you can do it. Those of you who'd like to stay and do it here with me and get help, you're welcome to. But any questions on how you're going to solve out this problem here? You're going to do it twice, remember, once for the triprotic acid and once for the diprotic acid. And for the diprotic, you'll need to write out that chemical equation. Any questions on how you're going to solve B? All right, so next up is C. So it says excess silver nitrates added to 14.04 milliliters of an unknown solution of HCl. So a lot of times students say, well, what's unknown about it if it's HCl? We know it's HCl. The only unknown part is the molarity, and that's what you're solving for here. So chloride was precipitated as AgCl, and the AgCl is dried and found to have a mass of 0.2758 grams. So you're calculating the molar concentration, which is just another way of saying molarity, moles per liter, for your HCl. So I've wrote out your chemical equation here. So you have AgNO3 plus HCl goes on to AgCl plus nitric acid. Here you know about the volume of HCl and you know the grams of your silver chloride. And I highly recommend you start with those grams. So starting off with grams of silver chloride, you're going to use a molar mass to get into moles of silver chloride, and then the mole ratio, and this is a balanced chemical equation as written, to get to moles of HCl. Once you do, moles of HCl on the top, and you need your volume of HCl on the bottom. So remember, volume HCl is right over here, but you do need to convert it into liters. So any questions on C? All right. And then finally we have D. So in D, you're going to take percent mass and turn it into molarity, just like I've written right over here. And I'm going to do the first one with you, but I still want you to write the first one out on your page. So when you turn it in, all of these should be in there, including that first one. So the first thing I did is copy the information. So this is acetic acid, and here's its density. This is its percent mass in this particular solution. So it's very concentrated, 95.6%. And just like when we were doing percent mass in class, you're going to assume that you have 100 grams. If you have 100 grams total, then you have 95.6 grams of acetic acid. This same number is your acetic acid so long as you have 100 grams total. And if you were to subtract the two, you would find the water. You don't need the water, but I just wanted to show you what else you have in solution. So any questions so far about this problem where we're assuming 100 grams and then we have the grams of acetic acid that is the same as the percent acetic acid? And actually where you did this, now that I think about it, was when we were doing our empirical formulas where you were given percents. All right, so we're trying to find molarity, which means we need moles divided by liters. So you're going to take the grams of acetic acid that you found above, and you're going to convert those into moles using your molar mass. And then you're going to take the total grams of solution, and it's got to be the total grams, all 100 grams of solution. You're going to use the density that's given to turn it into milliliters, and then you'll turn it into liters. And once you have your moles and your liters, you can calculate out your molarity in moles per liter. And by the way, these are all very concentrated solutions, so you are going to get high numbers like that 16.7 molar. I think we might even have an 18 or 19 molar in there somewhere. So just be aware you're going to get some pretty big numbers. All right, so any questions on anything here? All right, so I will post this up on our lab notes site, and the lab data, the sample data is already up there. I will be here till 9:45, so please feel free to stay and ask questions, or you're welcome to go and work on your lab on your own. Thank you all for coming. Have a wonderful evening. I guess I will see you on Wednesday. Bye, everybody. Bye. Bye, everyone.